Okay, last video of the course, and we are going to just go through the material on convexity. So the idea of a point could be any dimensional space. It's convex if you, whenever you've got 2 points in it, you've got the entire line segment that goes between the two of them. So the sort of thing that you could have that is convex is like a square, a filled-in square. If you take any 2 points in it, that's you get the whole thing between it. A donut shape, like what you'd call a torus, that's not going to be convex, because if you take 2 points on opposite sides, you to connect the two of them with a line segment, you'd have to go through the hole. So that's not going to be a convex. That's not going to be a convex shape. So we are only interested in the ones that are basically. So convexity. A shape in this works for n-dimensional space. A shape in n-dimensional space is called convex. I mean, when I say a shape, it's really just a subset. I'll just say a shape or subset in Rn is called convex if whenever you've got 2 points, let's say x and y, let's call this a shape S. Whenever x and y are in S, then the line segment connecting x and y is also in S. Okay, so what is the line segment connecting x and y? Well, if I've just sketch what I mean here, so if this is a point x1, y1, and this is a point x2, y2, then the line segment I'm interested in is this bit. And it's not too difficult to work out what the coordinates of all the things along here must be. You're just going to be taking a weighted average kind of between them. So I'll just write it down and you will see that it makes sense. So the line segment between they are all the vectors, if you're thinking of them as vectors, but the points t, x, so if this is x and this is y, tx plus 1 minus t y, where t runs from 0 to 1. Okay, so let's just see why that works. So not too hard to see. I'm taking a kind of linear combination of these two vectors, so I'm going to get a line. But when t is 0, so this x vanishes, and then I just get the y point, because if I put t in here, I just get y. So that just gives me y when I put t as 0, and then when I put t as 1, then this one vanishes and I get just back the x, which is this one. So as t runs from like 1 to 0, it traces out this line. So that's the line segment. So that's a nice algebraic way to describe it. What I'm just going to go through the various things that are in the notes. So first of all, some examples where we've given some already. So e.g. If you take the disk, so I take we know the equation of a circle is like, this would be centered on the origin. This is x squared plus y squared on the outside would be equal to like 1. If I want everything on the inside of that, I could take everything less than or equal to 1, and then I'll get all of the points that have radius, if you like, less than or equal to 1. So that gives me the disk. And that turns out to be, that's convex. And you can prove it's convex actually using this description. And you can just plug things in and check it, but we're not going to do that. So this is convex. So let's just go through these theorems. It's going to be, I'm going to do them quite quickly. So this theorem 8.02 in the notes, the intersection of two convex shapes is convex. Two convex subsets is convex. The proof is quite easy. If x and y are in convex sets A and B, say, that means that they're in the intersection. So it's exactly the same thing as saying that they're in both of them, as to say that they are in the intersection. Okay, but now A is convex, so it contains the whole line segment between A and B. So I'll put underlines there just so that we know that they're supposed to be different points. But A is convex. So A contains the line segment between them. Right, but the same goes for B as well. Similarly, so does B. But that means that the intersection contains the line segment. So the intersection contains the line segment. Okay, that one's done. Okay, I now want to just say that if we are taking the intersection of several convex subsets, then that works too. So a corollary. So a corollary is something that follows from a theorem, usually quite easily. But this one we're going to see how it follows by induction. So if A1 up to AN are convex subsets, then so is the intersection A1 up to AN. We could prove this directly, actually, and would be true no matter how infinite the number of things we were intersecting, but we will just prove this by induction. So by induction, we let B of n be the intersection A1 up to AN. If n is 1, then B1 is A1, because I just don't intersect anything apart from the A1. And we know that A1 is convex, so the B1 is convex. And then you know how this goes. We suppose true for n equals k. Then b of k is equal to a of 1 intersect all the way up to a of k. This is convex. That's by assumption. And now we have to use that statement to prove that the next one, b of k plus 1, is also convex. So b of k is convex from the theorem. So from the theorem we just proved, I've got one thing that's convex here, bk. I'm going to intersect it with another convex thing, ak plus 1. This is also convex. But this is just the intersection of a1 up to ak with ak plus 1. But this is bk plus 1. Hence it is also convex. So that's the proof, and so we've done it because we've supposed it's true for n equals k, and then we've shown that it's true for n equals k for plus 1. Okay, let's prove one more thing, which is that half planes are convex. And we're going to do this directly using the definition of the line segment. So theorem 8.0.4 is half planes are convex. So a half plane is just going to be any inequality that's any linear inequality. So i.e. If the subset defined by ax plus by and then any inequality here less than or greater than or equal to or whatever c. So that's going to be a half plane and that's going to be convex. And let's prove this directly. So I'm going to remember what a line segment is, take 2 points in this subset and then just see what happens. So let's suppose x1, y1 and x2, y2 are 2 points in the half plane defined by ax plus by is less than c. And the same proof will work here no matter what the inequality is, but we'll just assume that's true. Right, what does that mean? That means that these points both satisfy this inequality. So ax1 plus by1 is less than c, and ax2 plus by2 is less than c. Okay, so now let's think about the points in the line segment. Right, so the points in the line segment are, I'm going to write them as vectors because it may make it a bit easier to see. So x1, y1, I take t of those plus 1 minus t x2, y2. So these are the points in the line segment, and I can call that x, y, with t in 0, 1. So this is what so I can read off the x coordinate just by taking tx1 plus 1 minus tx2, and I can read off the y coordinate in the same way. So now I'm going to see if this point with these coordinates satisfies this inequality. I want it to. So right, so we check that with these coordinates, ax plus by is equal to, so I'm taking a of the x coordinate, so a t x1 plus a 1 minus t x2 plus by, so I take b t y1 plus b1 minus t y2, and then I remember that x1 and y1 and x2 and y2 satisfy some equations, so I can probably, some inequalities, so I can probably use those. So, but ax plus by therefore is equal to, so I'm going to factorise for t, so I get ax1 plus by1, right, plus I'm going to factorise for 1 minus t into ax2 plus by2, and then I have to just think. So I would like to plug in here less than c. Now I can do that, and the reason I can do it is because this t is always positive and the 1 minus t is always positive, right, or 0, right? If between 0 and 1, these are both positive. So if I therefore swap this number with something that is smaller, then, or bigger in fact, I'm going to make this bigger, then I will make the whole expression be bigger. So this is going to be less than tc plus 1 minus tc, and then I can just expand this and cancel, so this is less than c, and that's what I wanted to show, and therefore it is in the line, the half plane, so as required. Right, the last thing is just to say that if we're solving, as we were in the last lecture, a whole bunch of linear inequalities, so I'll write this as a corollary, the solution sets of simultaneous linear inequalities is convex. Right, why? Because if I've got linear inequalities, they are all half planes of some sort. If I therefore intersect them by the things that I've done before, by the last corollary, I know that those are always convex sets, and so the intersection always gives me a convex set. So that's the proofs in there, but I'll leave you to have a look at that.